Hello everyone, my name is Sarah Krieger and I will be your moderator for today's webinar. We will get started in just a couple of minutes. While you wait, please help us by responding to the poll question that will be on the screen in a moment. Hello again and welcome to today's webinar, PCB Routing. My name is Sarah Krieger and I will be your moderator for today. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you are unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we will do our best to resolve any issues. Everyone's lines are currently muted and will remain so for the duration of the webinar. This will be an interactive webinar with a few poll questions popping up throughout the presentation. Please take a moment when the poll questions are launched to provide some feedback to help us provide you with the most useful information. If you have any questions throughout the webinar, please type them in the question panel as they come up. We will have representatives ready to answer your question directly during the webinar. This is one of our largest attended webinars, so please be patient while we work through the questions that come in. The webinar will be recorded and posted on the EMA resource page. Once this is posted, we will send everyone who is registered for today's webinar an email with a link to the recording in the next couple of days. That being said, I wanted to thank you all for joining us for today's webinar and introduce to you our presenter, Rocco Calvello. He has been with the EMA team for 18 years and has expertise in PCB editing and routing tools. Prior to joining EMA, he held several positions in the design service industry, with a focus on designing for manufacturing, quick-turn fabrication, and assembly services. His design expertise spans 31 years. He will start off the webinar with an overview of routing and some common examples, followed by brief demonstrations. Assuming we have time at the end, we will field some questions in a formal Q&A. Thank you for your attention, and now over to you, Rocco.
All right. Thank you, Sarah. Welcome, everyone, to your Route to Design Success. And so routing is one of the most critical phases of a design, and approximately over 50% of total design time can be spent in the routing phase, and this was due to a Cadence user study that was done. So a very important part of the design phase. So the whole idea is to define your processes up front. So we would start with placement, get the placement approved, define our stack-up, define our critical nets and constraints. We would go in and maybe route those critical nets, and then we would, route the balance of the card. And then a final phase would be doing cleanup and verification. So the recommended process flow is to define your placement strategy, complete your placement and get it approved, set your boundaries. Now, what we mean by this is setting your route keep-ins, route keep-outs, via keep-ins, via keep-outs, specify any stack-up or impedance requirements for any critical nets, From there, you can define your constraints on those critical nets, whether they're differential pairs, matched length, impedance control, any special physical or spacing rules that you want to employ. Next step would be to generate fanouts for your signal and power connections, and then figure out your power distribution, how you're going to get power to all of the devices on the board. And this may, include split planes or power islands and things of that sort. Then we would route critical nets, like our differential pairs or clocks or match groups, etc. And then from there, we would go off and, do the bulk routing of the remaining nets. And then finally, we do cleanup. And we would, have a finished board at the end. So in the placement strategy, mechanical constraints, should be evaluated and implemented. So you would want all your mounting holes established, any mechanical cutouts, keep out regions, all of those things would be defined and looked at in the very beginning. Next would be your connector placements. Usually these have very specific locations because, they other devices plug into these things, so they usually have a specific place that they want them located, and once they're placed, you should lock them down with a fixed property so they can't accidentally be moved. Next step would be to place any large pin count devices, large BGAs, and et cetera. And using the rat's nest as a guide, you can look at those signals and you can such that you don't have any, you have minimized, the rat's nest twisting or crossovers. The whole idea is so that you get a smooth signal flow out of the device so that you can easily route it. The parts should be grouped together by function, and the rat's nest can be optimized for routing so that the devices are close to each other and your nets can be very short. This is where room properties will help you back in the schematic tools. So room properties allow you to group those parts together and then allow you to place those parts by room so you can gather all those parts that belong to each circuit. Then the last part would be placing all your decoupling caps, and obviously we would want to place those in close proximity to their device power pins to increase their effectiveness. So as far as placement grid, the parts should be placed on the coarsest grid based on the pin pitch of the majority of the parts. Now, I understand that there's a lot of mixed technology on boards. There's, might have imperial units for some parts, there may be on a 50 mil, pitch, or there might be, some metric components on the design as well, some 1 millimeter or less. So we always have these mixed technologies. So a good rule of thumb is to look at the majority of the parts in the design and evaluate their pin pitches, and then use that as your guide for your grid to place your parts. And the reason why we want to place them on the coarsest grid possible is because our routing grid will be a derivative of that. So for example, if most of the parts have a 50 mil pin pitch, then the routing grids could be as follows. It could be a 5, 10, 25, or even 50. So all of these, routing grids are divisible by the placement grid. So complex parts can be also achieved at the library level. And here I have an example of a 0.65 millimeter pitch part. This is a BGA, a typical, what we would call a dog bone pattern, where it fans out in diagonal mode. Does not work in a situation like this. So this is where you can come up with your own pin escape scheme to figure out how to get these signals out to a routing point. The orange dots that you see are actually the vias. The green ball is the ball of the BGA. So you can see the actual vias are larger than the ball grid array pattern. So in this particular case, the grid is a derivative of the 0.65 millimeter pitch, and that's how we get this pattern. And you can see I can easily route to this part now. And this is really advantageous because what if I have multiple parts that use the same package? So once I figure out the pin escape scheme, I can incorporate this into the library footprint. And it has no effect on the schematic. A lot of other tools, these vias would become another pin, and I would have to double the pin count of the symbol to accommodate that. We don't have to deal with any of that. We simply see this as a BGA with a via out, extended out on the end. Next thing is we would define our keep in and keep out regions. So you may have special connectors that have metal shells, or you may have cutouts in the board, where I want to prevent any traces or vias to route through those areas. So I can block those with keep outs. The route keep in we establish keeps the copper away from the edge of the board. So we'll define a route keep in area to keep any copper planes that we add or any kind of routing will stay on the perimeter of that route keep in. You also need to be mindful of your assembly requirements. You might have V-scores, you might have break-off tabs, fiducials, different items on this board that are related to assembly that you need to be mindful of. So you also want to take care in defining your stack-up. So the stack-up, can have a direct impact on your differential impedance and your single-ended impedance based on the dielectric constant of the material that you're using. You should also model your impedance targets before you go with that stack-up. And this may entail working with your board shop, your fabricator, because they may have specific cores that they stock for a build. So you would always want to send your stack-up to your vendor and have them approve it, because they're the ones that are going to guarantee that your design meets the impedance requirements. So inside of our cross-section editor, you can go through and you can model some of this stuff based on the dielectric. And here you can see we're modeling a differential pair that's edge coupled, and you can see we have a modeled impedance of 86 ohms. Differential pair parameters are defined in, hopefully you're using a constraint manager like we have in our tools, and they're defined in our particular case in the electrical domain. Length rules can be defined for your match group and critical nets. They're on a worksheet by themselves called total etch length in this case. And then of course you also need to be mindful of your physical trace widths and your spacing rules and your via size. And this will be determined based on the board density and your current requirements for any power devices. So if it's a really dense design, you may be looking at like a 4 mil trace in space with like a an 18 mil via with an 8 mil drill or something like that. Some of your higher current devices will have, of course, wider trace widths to accommodate the current, and even larger vias to sync that current. So all of these things need to be taken into consideration when you're doing your design. So fan-out vias are used when designing multi-layer boards, and fan-out vias for single pins allows access to multiple signal layers for routing. This also provides additional space and routing channels for designs with those increased density and pin counts. The fan-out vias for power must be established for power distribution and to ensure that they complete connectivity to their inner plane layers. We can also utilize split planes, and split planes will allow us to save real estate or layers, allowing us to provide power distribution on less layers. So if you have a large area that you can use to pour some copper to allow for your plane connections, this works quite effectively. You can assign different colors to your different nets so that you can establish where they are, and that will help you define the boundary that you put in for the different split planes. And in this screenshot here that you see, we draw this boundary with a line on anti-etch layer, and it's usually at least, minimum of like a 10 mil split. So that line width would be at least a minimum of 10. You may require, in some cases, if you have a high voltage section on board, you may want to increase those, to be quite large. Maybe it's a 50 mil air gap in between there, so there's no arc over. Critical nets are then routed in the next phase to meet any impedance rules and timing requirements. We have an interactive timing meter that turns green and red. Red is fail, green is pass, and so it gives you a dynamic timing meter to let you know when you've reached the target. Another common design practice when routing critical nets is not to route high-speed signals over plane splits. So you want to make sure that it's sandwiched in between some solid planes, or if it is a split plane, make sure the signal, that high-speed signal doesn't cross any of the splits. Because why? It causes impedance discontinuities that impact the signal integrity. So in this particular case, this clock net routed over this split will cause a signal bounce in this area and will affect the signal integrity of this signal. We also have a check in the tool called segment over void, and that will highlight any violations as you see here. So great, all my critical signals are done. Now what? So I would go on to the bulk routing, and decision would be made at this point. Okay, how do I want to do this? So what's the best use of my time? Maybe consider an auto router. I guess it depends, right? How large the board is, how many connections, how much time you have to spend on it. A lot of people are very torn on the subject of auto routers. So, they'll say, it takes too much to learn the auto router. I don't have time. Results aren't good. A lot of people won't take the time to learn the tool, and they'll, set a couple controls. They'll launch it. It looks absolutely terrible, and they say, I can do a better job by hand, and they abandon it. Another retort is I'll spend too much time doing cleanup. And the route quality may impact the performance of the design. So if it looks really bad, that may be true. However, you can get a good result with an auto router if you control it correctly. So here are some of the pros and cons. Auto routing can be fast. I can try many different strategies real quickly. It can also see if the board is routable based on the number of layers and the constraints that I have. So this allows me to try a couple what-if strategies right away. And of course, if it's a good solution, it's reusable. I can use it on other designs. The downside is it's less granular. I don't have as much control because it's automatically doing it. If I have ECOs down the road, it might be a little harder to implement those with using an auto router. And it's difficult to convey user intent sometimes because the router if it sees a routing channel and it meets the criteria, it'll blast a trace through there, and that may not be the ideal place that you'd want that trace to be routed through. So those are the downsides. The manual routing, you have a lot more control. You don't have to plan as much ahead of time. You can adjust to changes or ECOs on the fly. However, it takes a lot longer, and it can be error prone, and you have a lot less time to try different strategies. So these are the things to consider. So ultimately, your goal is to finish the route effectively, making the best use of your time. And routers are just tools. Use what works best for the job at hand. So what kind of route defects after I route the board? What kind of things should I look for in the cleanup phase? So here's a few. So 90-degree corners, we would not want those because they become acid traps. And at the board shop, what will happen is you'll get etchant trapped in this 90-degree corner, and that will cause reliability issues because the etchant never gets completely cleaned away. Here's a non-ideal pad entry. We have the same sort of situation. You see this acute angle here, which material can be trapped. And same here in this situation with the surface mount pad. We also have additional checking that we can do. We can look for parallel line gaps, uncoupled differential pairs. We can look at different arc radiuses or miter corner sizes. So these are some additional checks that our tool can look for now. So manual inspection, is often what people would do, right? They would just go through layer by layer and look for defects. This can be tedious, and depending on the size of the board, it can also be error prone. What if I miss something, right? So ideally, your CAD tool can provide some things or tools to help you identify these problems. So one of the new things that we have is this thing called Route Vision. And Route Vision has a bunch of different checks that you see here. And as you hover over each one of these checks, it gives you a description of what this check does. So you can see we can look for, parallel lines with a gap less than a certain amount. That would be important because if we have some long parallel lines, that could introduce coupling or, signal coupling or crosstalk, right? So that may be a bad thing depending on the design. Also, non-optimized segments, uncoupled differential pairs, and all of those other checks that I mentioned in the previous slide. So here we can turn on the route vision. We can configure what we want to check. We can also implement a dynamic log, which shows us any errors that it comes up with. So here are, once you can find them, they're easy to fix. So here I have some examples. The highlighted yellow here is what they call non-ideal pad entry, which means it's not coming in at necessarily the correct angle, or the jog, this jog here has to be a certain distance away from the pad before it makes that jog, otherwise it reports it. Another very important thing is DFM. So you want to make sure that your design's manufacturable. And hopefully, your CAD tool can provide you a way to embed DFM rules and checking right into the design process. So some time ago, when we would generate our design data, we would send it off to our fabricator, and they would run it through Valor or some tool like that, and they would do and analyze the design, and then they would come back with a list of manufacturing defects. They would provide them back to the designer. Designer would go and correct those, and then resubmit his data again to be looked at. So it's this constant loop until we get a clean manufacturable design. So what if we could take those same defects that they're looking for and we can put them right in our tool? So right now in our constraint manager, we have manufacturing rules that we can apply, and we can find these things up front before we send the data. So it really can cut that loop of going back and forth to the fabricator down significantly. We also have a real-time in-design DFM webinar that we did, so you can look for that for more information. So with that, I think I'm going to turn it over to Sarah for our next poll question.
Yes, please answer the next question. I'm going to put it on the screen in just one moment. Okay, and back to you, Rocco.
All right, thank you, Sarah. So let's take a look at the design here. So let's open up a board. So here's our design. So I've got my board placed. It's been approved. I've got some copper pours for some of these high current devices done. The next thing I want to do is start establishing, my route keep-in boundary. So the way I can do that is I can go into this command called zcopy, and if I go to my route keep-in group here, and I'm going to contract this by 25 mils. So I'm going to tag the card outline, and I now have a barrier you see in orange there that prevents any copper from going beyond that boundary. So that's very important, especially when you get to pouring copper planes. You don't want those out on the edge, because if this goes into a chassis and they're out on the edge, they can get actually shorted together. So that's one of the reasons, that we don't do that. So once we've established the route keep-in, the next thing would be to finish any fan out of any components that we have. So let's go ahead and create some fan outs. And I'll tag this connector. Over here, I'll select the BGA quadrant style. And I've got two BGAs here I'll fan out. So now I have all my fan outs ready to go. The next thing would be to define my split planes. So let's go through and we'll use a command called split plane create. And I'm going to first select the first layer in the stack-up. So this is my ground layer. So it's already poured the ground plane. I'm going to use my net filter here, and I'm going to select the net I want to tie that to. So if I turn on this layer, you'll see it. So there is my solid ground layer now. The next thing would be, let's take a look at the next layer. So I have a 3.3 volt plane, and this one's a split plane as well. So let's go in here and create that. So this is a net called M9V. So you see in blue around that island, that's my anti-etch. That's what determines the split. And this is going to be 3.3 volts. Okay, so there's my next one. My ground earth, I'll do another one. And this one, this small section inside the BGA, that's my 1.8 volts. This is my 12 volt section. And then the last part of it is ground earth. So I'll go ahead and select that. And then I have one plane left here. So we'll do the last split plane. And this one's going to be 5 volts and then 2.5 volts. So now all of my power distribution is done. The way I can easily check that is if I go into my display status. If I go to my unrouted connections, these traffic buttons are live here. If I select that, you'll see I'll get a report of all the unconnected nets, and they're alphabetical. So if I look through here, I would look for ground or any of my power nets. So you can see these are all signals at this point. So all my power distribution I know is now taken care of. So now I don't need to worry about that. So the next thing would be is I need to start looking at my critical signals. So let's go up here and look at these differential pairs. So if I start to route, my differential pair rules are defined in the Constraint Manager. You notice as I start to route, it automatically gathers those together as a differential pair. And you also notice I have a dynamic timing meter. So I'm going to route this in. And you can see I have an electrical length DRC. So I'm going to use my slide command, and I'm going to use my timing meter as a target. And I'm going to make it a little bit longer than that. So that one now meets the timing requirements. So let's do the next one. And this could be a little tedious, take your time. Let the tool work for you. And same thing here, I'm going to grab and tune this the best I can. I'm probably going to have to add a little delay to this one, so I'll use the delay tune here. And again, I'm just using the timing meter to help me. And now that's tuned. So let's do the next one. And I'm going to back up a step here so I get a better entry. Now this one also has some electrical length issues, so let's go ahead and tune him. Now this one's a little bit more interesting because what's occurred here is this fan out is a little bit longer, so I have a phase problem with this one. So what you can do is you can use a thing called phase tune here. And over my options, you can add a parameterized bump. So you can go through and you can dial with these settings, and it'll show you the overall bump size that you're going to get. And then you can strategically place, where you'd want these. So I'm just going to add a couple bumps here. And now you can see that phase now is now matched so that those are correct now. So if I go in and I route my clock, just going to route my clock net in here. And of course, there's some delay on this one as well. So I'm going to add some delay here. And I'm going to try to utilize space that I know. This is my routing point, so I know the route is going to come in to these pins. So I'm going to try to utilize some of this space in here to add my tuning. And I don't really want to make them any longer than I have to because I want to save, some routing real estate. So now that's complete. Let's do the last one. And we'll add a little bit of length. So I'm just using the timing meter. And the timing meter is going to tell me when I've achieved the target length. You'll see it'll turn green. So I'm in the target area now. So now my criticals are complete. So now I would make a decision. Do I want to try to manually route this, or do I want to auto route it? If you look at the connections, you can see where they all are. So the heaviest traffic is going to this FPGA. So from this point, I'm going to choose to auto route it. So I'm going to go to the auto router. It's passing all of the rules. I've killed a log file here. It's passing all the rules from the constraint manager over to the router. And I'm just going to change these colors so it's easier for viewing. And now the board is ready to route. So you can run this tool interactively. You can launch commands from the command line. There's pull down menus that you can execute, or you can put together a little script file of your own with just some basic route instructions. And it's called what they call a do file. This is what I want it to do. So I'll grab the do file and I'll launch it. Now it's giving me a warning here. It's saying that, hey, this version of the router with OrCAD Pro doesn't support any differential pair routing, but I've already routed those as critical nets. And before I launch this, you'll see they kind of have like a white line through them. This means they're in a protected mode. So any of my critical nets cannot be altered by the auto router in any way. So those are protected. So I'm going to ignore that. Now what's going to happen is this board is going to attempt to route all of the connections in the first 5 routing passes, and it doesn't care how it achieves that. So all those yellow markers that you see are what we call conflicts. So after pass 5, if it's achieved 100% connectivity, which it looks like it has at this point, it's going to go through and it starts to resolve those conflicts. And the conflicts are crossovers where traces cross over one another, and also clearance violations. So we'll run a number of these passes, and the algorithm changes with each pass. It does rip up, retry, shove, until the design converges, until all of those conflicts are gone. So we're down to, it looks like it ripped up 2 connections to resolve some of the conflicts. And this may take several phases of route passes. If it completes in less than the routing phases that you've defined, it will continue on, so it doesn't have to run through all of them. So we're down to 4 conflicts and 2 unconnects if you look at the status. So it resolved the last unconnect, and it's working on these last couple conflicts. And it should converge here. So you can actually get a really good result. This can save you a huge amount of time. I mean, if it's a large design, maybe it has 10,000 nets to wire, chances are your manager's probably not going to give you the luxury of, spending the next 2 months routing it. So an auto router, can really help you. So it's running some clean passes. It's running another route phase here. And I'm thinking it should converge here soon. You'll also notice that the router itself routes in an orthogonal mode. So the mitering of the traces isn't done until the very end. So that's actually when the beveling occurs. Okay, so I've got 2 conflicts, so I would have to go back and look at why this was blocked. Maybe I should have moved my clock trace a little higher. But I mean, this is real life. This is what could happen. But you can see I've got a really high completion rate here. I could easily go back there and tweak that and then get this to converge. But for demo purposes, I'm just going to save this. So if I save this session, I'll go ahead and save it. And then I'll quit the tool. It also records all the things that you did. If you want to see what the router did, you can retain that. I'm going to quit. And it's going to come back to my board, and it's going to converge that routing in. And here you can see those DRC markers of where that occurred. So now I could start to look at issues with the design. So again, I can go through here and I could start looking at it layer by layer and critiquing, the design and looking for defects. So this is where the route vision can help you. So if I go into the vision manager, you'll see a new tab appears over here, and I'm going to select the route vision. And in here is the configuration. These are the different checks that you can employ. And you see by selecting each one, like this one's non-optimized segments. So you see in red above in the screenshot where they're kind of skewed toward one side of the pads in that channel, where the purple ones down below, it centered those traces in between those pads. So that's what it's optimizing. And these different checks show you what it's looking for, and then so we're looking for 90-degree corners and things like that, or minimum miter corners. So these are all the different checks that you can employ. You can also pick a color that you want to highlight the errors in. And there's also a dynamic log. So down here below, you can see I have some 90-degree corners that the beveling in the router did not achieve. So there are things that we can do here too. So under the route menu, we also have a menu called gloss. And if I go into parameters, I'm employing a couple here. So there's line smoothing, and this will convert any 90-degree corners to 45s. Also, if maybe you did an ECO on the board and you had a little piece of, dangling etch out there on the board that you didn't know about, you can also have it look for those type of defects and remove them. So then we do like centering of lines in between pads. This one improves, pad entry. So we come into a pad at a 45-degree or a 90-degree angle. So whatever checks that I have selected here will run these routines. So we'll go ahead and gloss this. Also, an important thing to mention here is like my critical nets, my clock lines with differential pairs, I don't want gloss to modify those in any way because I've already done those. So you can apply a property called no gloss to any of your critical nets, and then those nets will be immune from this run that I'm doing here. So you can see it's going through, it's cleaning it up. It doesn't get completely everything, but you can see I have some non-ideal pad entries. So if I zoom in here, for example, it doesn't like the amount of distance coming out of this pad. So what I can do is, if I want to fix that, I can extend this out a little bit more. And you can see now I've solved that defect. Same here. If you look at it's not coming in at a 90-degree into this pad. So you can kind of go through. Now, my differential pairs, they come in the pads at an angle, but I want to maintain my coupling. So I don't really want to change those. But it is showing you that, hey, it's not exactly coming in, at the best angle that we believe it should. So, use this as your guide. If I go to the second layer, and this is dynamic, so whatever layers that I have turned on, it's going to now show me those defects. So you can see just by extending it coming out of that pad a little bit more, I can solve that defect. And here, if I look, maybe if I shove this trace up a little further, I could create a route channel and I could resolve this conflict. But it looks like possibly my clock line may have blocked the channel down here. So these are things that you can evaluate. So once it's all complete, then you can start your manufacturing setup. And if it passes all your DFM checking, then you're good to go. So I also have another thing I want to show you. But prior to showing you, I think Sarah has one more poll question. This is managing, if you have lots of, high-speed buses, or you have, different, DDR byte lanes or things like that, where you want to control the tuning. We have some tools that will really effectively work on these large bus structures, which I'll show you in a moment. So I'll pass it over to Sarah.
Thanks, Rocco. All right, here comes the next poll question. All right, back to you, Rocco.
All right, thanks, Sarah. So let's switch gears here a little bit. I'm going to open up another database here. And this particular database, I have a byte lane here. And I'm going to change my tool. So I'm going to choose Allegro Designer and the high-speed option. That's where this feature resides. And I want you to think about this for a moment. So if you have a byte lane such as this, and these all have, delay DRC markers on here, you can see them. And it's a match group, so it's tied to a particular target that I'm trying to achieve. So if I'm going to do this manually, this could take me a little bit of time to do this. I would have my dynamic timing meter to help me. I would probably have my constraint manager up on another monitor, and I could look at that whole group and I could see what the target lengths and stuff are. But what if I could take and I could paint the constraints on the screen so I could visually see them? So we have a thing called timing vision. So timing vision, if you look in the options here, this gives me a legend, and I can set these colors to whatever I want, but you can see there's going to be a stipple pattern applied to the critical signal, that the target of this group. So if I swipe a window around this, and you can see now I've applied those constraints visually. So now I can see by color code exactly what's going on. So what I can do is I can employ this thing called auto interactive delay tune. So what this does is I can just swipe a window around this whole byte lane, and it will tune this entire section for me based on my constraints. And it's kind of odd, whenever I see this, you see the progress bar, it kind of slides back and forth. But it'll come up with a solution here in about 30 seconds. And this is just one byte lane. Typically you have many byte lanes, right, that you're working on. So imagine how much time this could save you if you're doing these large type of designs with all of these timing restrictions. So this can help you quite a bit. So it should finish up here real soon. So now it's applying the changes and the solution that it found. And you'll notice even on the diagonals, if it runs out of real estate to add some delay, it will actually utilize the traces on the diagonal too. So there's my entire byte lane that's tuned within probably less than a minute. Just to kind of show you how critical this is. So this is my critical trace here. So if I went in here, let's say I added a phase bump, watch what happens. So just by skewing that one net, I've clobbered that entire section. That's how critical it is. So that just kind of gives you some idea. Another thing that we have is auto interactive phase tune. So imagine you have hundreds of differential pairs. I've seen some really large designs that have a lot of differential pairs, and typically you'll route them in point to point as you see here, and then you'll go in and solve any phase mismatches. So we have another tool here called auto interactive phase tune. So again, I have some parameters here that I can adjust. If I swipe a window around that, you can see it resolve that one. Now I'm going to back out of it, and I'm going to show you could also do groups of them. So if I wanted to, do a group, I could do that. Down here, this one's a little bit different. This one, you see the pin fields are further apart, so I have a much more pronounced, delay issue here, phase delay. So I'm going to go ahead and tune that. Now it tried to shorten this one as much as it could, but this one is still too short. This one is still too long. It tried to shorten it, but it could not get it. So I'm going to allow an uncoupled bump here, and I'll swipe it again, and now you can see it added a little phase bump here to finish matching that. So that's auto interactive phase tune. So with that, I guess I'd just like to close with, routing is one of the most critical and time-consuming phases of the design process, and with the proper process in place and the knowledge and the tools, you can achieve a good routing result. So I'll go ahead and pass it to Sarah and see if we have any questions.
Thanks, Rocco. Please enter any questions you have in the chat now. If we are unable to address your questions immediately, we will be in contact with you. And just a reminder to all attendees that this webinar will be recorded and posted on the EMA website within the next few days. Okay, Rocco, so our first question is, what is a good split plane spacing gap to use?
So a good rule of thumb is at least a 10 mil or larger. Obviously, the larger you can go, the better. So if you have more spaces in between the pin fields where you can place a split, usually a 10 to 15 mil split is typical.
Okay, and what is adjacent layer keep out in pad stacks used for?
So adjacent layer in the pad stack editor, you can actually define keep outs under surface mount pins, and it's called adjacent layer keep out. And what this does is it basically keeps the impedance continuity underneath the pad. It prevents any kind of routing directly underneath the pad, on an inner layer. So it maintains those impedance values.
Great. So do route keep outs ban only traces, or does it ban both traces and vias?
So route keep outs, so we have a couple different kinds of keep outs. We have route keep out, we have via keep outs. A route keep out will ban either traces or vias. The route keep outs can be layer specific as well. So if you only want to ban, traces going through a certain area on, say, the second internal layer, you can define those barriers by layer. But as far as routing keep outs, it includes vias as well. Where vias, a via keep out will ban vias, but I could have traces running through that area. So it really depends on how, what you want to control.
Are vias and pads permitted?
I'm sorry, what was that?
Are vias and pads permitted?
Are vias and pads permitted? Yeah, so again, this is something you would probably want to check with your manufacturer who's going to do your assembly. Typically, if you have a via and pad, those vias will tend to suck solder down through the barrel and into the via. Depends on the process. You may have the vias filled before assembly. At fabrication, maybe they're plated shut. But if you do via and pad, again, check with your assembly shop. We allow it. You can do it in the tool. You can also have requirements where you require the via to fit centered inside of the pad. So those are the only things that you would need to consider. We also support blind and buried stacked vias too. So if you're working on a really large and dense design and you need to preserve all your routing channels and the board is already utilizing blind and buried vias, you can stack those together. So, for example, if I had a via that goes from layer 1 to layer 3, and then I have another via that goes from layer 5 to 7, I could bind those together and stack them on top of one another because the drill never passes all the way through. So by enabling me to stack them, that gives me additional routing channels and space clearance that I can effectively route more traces in that area. So I'm not taking up as much via with, as much space with the via by doing that.
Okay, will the PCB layout function from a hierarchical schematic? How will it handle component designators where there are repeated sub-hierarchical elements are used repeatedly?
So everything in our tool is netlist driven. So those reference designators, every part on the board will have a unique reference designator. So back in your schematic, when you set up your hierarchy, you're going to annotate your schematic, and the annotation will ensure that each of those hierarchical blocks and the sections that are below those blocks have a unique reference designator. So actually, when you're placing the parts at the board level, they already have that resolved.
Would it be possible to show one of the windows where you input the constraints?
Sure. So if I go into the constraint manager, this is what the constraint manager looks like. So we have an electrical domain. Now, I'm in the Allegro version here, so maybe what I should do, because I have some additional things here. So let's just hop back down to Pro for a second, because I think most people probably have OrCAD Pro or Standard. So this is a little bit more representative of what you would see. So if I open the constraint manager, you can see I have these different worksheets. I have wiring, which allows me to set topologies, like if I want to do daisy chain or star routing. I can set up, impedance rules here. I can set a target impedance. And as I apply these rules down here to the net list, like here you can see I have a net class defined. I have some differential pairs here that have a reference rule. So you define the rules up here and you apply them to the net list down below. So these are where you would set those rules. So I have, like I said, a differential pair rule here. So this is my diff pair rule. And if you go down to the worksheet, you can see those are applied. So that's the electrical domain. So this controls all of my electrical constraints, timing, match group, impedance, those sorts of things. These could also be exported. So you could export these constraints from this design, and maybe you have another design that's going to share a lot of these same rules. So you don't have to recreate these constraints. You can export them, and then you can import them on the other side. Down here, the next domain is what we call physical, and this is where you would set your different physical rules. So if I have a power rule, for example, I want a wider trace width for power, and I want a larger via, here I can go in and I can establish what those trace widths are going to be, what the name of that physical constraint set's going to be, and then I would go down simply to the net list, and then I would, here you can see this offset 1 is referencing that rule called DPDR. So you can see, if I expand this, you can see those rules are now applied from that referenced electrical C set. And then the same with the spacing rules. The spacing rules, I would go in and add any of my object spacing here, my line to line, my line to through pin. I could also add additional rules here. I just have default in this database, but you can also set these by layer. So if you had different clearances that you wanted to set by different layers, you can do that too. And then we also have what we call region rules. So maybe I have different spacing rules inside of maybe the region of a BGA. Maybe the clearances are a little tighter there, and I can establish a region around those parts. And anywhere inside that region, the rules will change. Maybe the trace width goes from, maybe I'm using a stock, 5 mil trace in space. Well, inside that region, I can utilize like a 4 mil trace in space because the pin pitch is tighter and I need to be able to get into the device to route it. So that's what all of these rules are here. We also have same net spacing. Same net spacing is typically used in the manufacturing realm. So all of these objects are on the same net. So maybe I want the first via coming off the surface mount pad. Maybe I need it to be away from the surface mount land pattern by at least 10 mils so that I don't suck solder paste off of the land pattern. So these are typical same net, DRC rules that you can set for manufacturing reasons. And then down here is the manufacturing domain. This is where we talked about the DFA constraints and the design for fab constraints. So these, we can look for like annular ring and different copper features, acid traps, different spacing rules to different objects. And then we also have a design for assembly group as well. And then we also have design for test now too. And then last but not least, we have properties. So here, this gives you all the properties in the database. So it gives you visibility to all of those, whether it's a general property or if it's a routed property or a component or pin property. So this will show you or make visible all of the constraints that are in the design. So I hope that answered some questions.
Just one more. Does route keep out include poured copper?
Yes, it does. So any route barrier will be looking at copper features. So if it's a pre-routed or I should say a pre-poured copper plane, then maybe it's on a specific layer and maybe you ban the routing above it on the next adjacent layer or below it on the next adjacent layer. So but if you have copper pour inside of a route barrier, you will be flagged with a DRC. It won't prevent you from doing it, but you might light up the design with a bunch of DRCs. And if you're okay with that, you could also waive them so that you get them out of the main DRC list, because the whole purpose in waiving things is things that are known design violations that occur. For example, you might have a connector that overhangs the edge of the board. Now in this case I don't have one on this board, but you might have a connector that overhangs the edge because that's by design, right? Well, if it crosses my component keep-in, of course that will show up as a violation. So I would waive any of those known DRC conditions to get them out of the main DRC list, because what I'm trying to prevent is when I look at my regular DRC report, I want to make sure that I'm only looking at real problems. I don't want to have a whole list that I'm sorting through and I review it and I say, okay, this one's real, this one's not. Because if I have to start sorting through that list, now I'm in the danger of missing something that's a showstopper. So if I can eliminate the ones I know aren't a problem and put them in a waived report, then when I'm looking at my DRC report, all I'm looking at are real DRCs. And at the end, I can also review the waived report too and make sure that I didn't waive something in there that shouldn't be in there too. So that's the purpose of it. So, but to answer your question again, if you have a route keep out, it does look for any copper violation in that area, and that includes copper pours.
Alrighty, thank you, Rocco. Looks like we have a few more questions still coming in. Unfortunately, though, we are out of time for today. However, if anyone has questions that were not addressed during the webinar, we will be following up with you on an individual basis. I will be closing the webinar now, and we will be sending everyone a recorded version of today's webinar with the slide deck within the next few days. Thank you for taking the time to join us today. Bye-bye.
Thank you all.